Jones. Thank you, ma'am. So let me turn off my Eclipse. Okay, so somebody's got a question from the quiz from 1B. Very good question. There were many different versions of the quiz, so if this is not the same problem you had, well, I'm not going to do your problem anyway. I'm going to do a problem nobody had, but everybody had. All right, let's see how close I get. Pretty good. There I am. All right, yay. All right, guys, so on, what was it, 1B, correct? 1B. Much everybody had a problem a little bit like this. Some of you guys might have had sines and cosines or something. All right. We're getting as far through chapter 10 as we can. I don't know if we're going to finish it today. Yeah. So we're starting with 10.6, I believe. We got a little bit into that last time, parametric stuff. All right. Yeah, so what the shit do you do with this? So if it's not a identity like sine squared plus cosine squared or cosine squared minus sine squared or something like that, I normally want to try to get my trig stuff together, interacting with each other. So I mean, what do tangent and secant have in common with each other? Does anyone know? What does tangent and secant have in common with each other, besides they're both trig functions? Yes, cosine. What about cosine? This is sine over cosine. This is 1 over cosine. So you can take a 1 over cosine out. You guys with me out there? Did I get this thing right? No, I should have done it the other way around. Oh, that's right, because that's right. Let me make this a little bit different. 1 over. There we go. I'll be able to get somewhere now. So I changed this up a little bit so it wouldn't be the same as anybody's. And I have one extra little thing I had to do. So can somebody tell me, all right, how do you guys feel about what I have done so far with this? Some of your 1Bs was easier. Some of your 1Bs was easier than this because your 1A was harder. So I try to make it play off each other a little bit. Some of you guys had just a cosine and a sine. You can make a tangent out of that if you divide them. Easy peasy, right? So here I can take a 1 over cosine out. Is that cool? Dan? Can 1 over cosine ever equal 0? Well, yeah, but that's the thing. You're not doing this problem. You're doing the problem I gave you, in which case the square root of 2 makes sense. If you do the problem, you'll see what I mean, because everything's upside down in your problem. Yeah. So 1 over cosine cannot be 0. So now I got sine x equals negative 1 over rad 2, which is negative rad 2 over 2. And that's one that you know the angles for that. You know the angles. I love it. Some of you guys made the mistake of not answering the complete question. I said find all solutions and then find solutions inside of 0 to 2 pi. And some of you guys just did one of those two things. All right. Any Is that all right? Anything about that? Hey, all right. Okay, so number 6. Let me see. Oops. All right, you're gonna work. Here we go. Oh yeah, that was that one. Oh, how can I say it? Number 6 is kind of related to what we just did. If I had this, how would I try to change this into rectangular? What do you wish was sitting next to the sine? Well, how do you go from polar to rectangular? Very easily. If only there was a what next to the sine, I could become something straight up. There it is. What do you wish was sitting next to the sine and would equal one of the rectangular coordinates? Yeah, if only there was an r. I can make that happen. Really, I don't have to multiply top and bottom by r, because this r is just like, come on up here. All right, so that was the easy version of number 6. Some of you guys had a problem like this. I love this problem. So, I mean, just to give you a little clue, this is 1 over cosine. This is 1 equals 7 cosine theta. Now, to be honest, there's a lot of different ways to do this problem. There's many, many, many. One way to do this is to multiply both sides by r, because then you know what this is. And if r squared is x squared plus y squared, you know what r is. All right. Both of them have that same idea. If only there was an r there. All right, let me stop for a minute, because if I had an r sine theta sitting there, y, easy. If I had an r cosine, that's x, easy. If I don't have that, but I got a cosine sitting there, I want an r to be there somehow. If I have a sine sitting there, I want an r to be there somehow. Of course I do. Some of you guys, for some reason, thought that cosine theta equals x. That's a little crazy, right? We know better than that. Cosine theta is a ratio. Can't just equal x directly unless it's in a unit circle. And I don't know if it's in a unit circle. Okay. Anything else from quiz or homework? All right. So if not, we're going to keep on going then, everybody. If you haven't looked at your quiz yet, they're graded. Take a look. I haven't updated grades yet, like your overall average. I haven't updated that yet. Sorry, I'll get to that eventually. All right. So I really want to make sure no questions before we get back into parametric equations. No more questions. You guys are good. I will believe you for some reason. Okay. All right. So let's get back into drive me a little crazy. All right, I'll do it. This is such a, so I kind of want to come back. All right, there's a lot of different ways to approach this subject. This is such a different idea. And there's going to be one level of this, which is just kind of like playing around with shit, which is what a lot of math feels like, and a lot of math is. But this opens the door to so much stuff. It's insane. What do you think? If I wanted to, let's see, how do I want to say this? So parametric equations enables us to do some stuff we could do with polar, but we're able to do even more stuff than polar can handle. So parametric equations, here's the idea. So the concept behind them. Jeff, you can get it. There you go, buddy. All right. And I got to tell you this. I have a little like keychain Etch-A-Sketch. You remember we talked about Etch-A-Sketches? And it came to mind. I was like, I got a keychain Etch-A-Sketch. And I don't know why. I have no idea where it is. I'm like, it's a keychain Etch-A-Sketch, Jeff. What do you mean you don't know where it is? That kicks so much ass, but I have no idea. I think it might be in my office, which actually I'm pretty sure it is. All right. Anyway. Oh, this is so cool. All right, let me do this. I did find this. Let me show you. I found an online Etch-A-Sketch, which is not great, but it's gonna be fine. So in case you have no idea what I'm talking about, there. Etch-A-Sketch, yes? And I wish, the only thing is we don't have knobs. So I need you to go with me on this. So if I turn this knob, it would do, all right, now it's not doing anything. Why are you not doing anything, chat? Oh, the Bob Ross one, yes, exactly. All right, for some reason, there we go. Let's see if this is back. All right, good. So let's pretend, I can't remember which is which, to be honest. Let's say this is the one that controls the vertical. So if I turn the knob one way, it goes that. And if I turn the knob the other way, it'll go that way. Is everybody with me? That's amazing. So that is the X-axis controller. Yes? All right, now watch this. It's kind of cool. Shake, 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 shake. Sorry. If I turn this knob, it'll go up and down. It's the Y-axis controller. I'm going to pretend like I'm actually turning the knob. All right, so if I turn them both at the same time, of course they go at a diagonal. Are you guys with me? I really want you with me because this idea is so cool. All right. The unfortunate thing here is I cannot control how quickly I turn the knob because I'm actually using my freaking arrow keys on my keyboard. So I can't control how quickly I turn the knob. But if I turn this knob twice as fast as this knob, would it go at a 45-degree angle? If I turn this knob, so the X direction, twice as fast as I turn the other knob, would it go at a 45-degree angle? No. Does that make sense for everybody? All right, so let's take that a step back. So what we're saying right now, let's see, I can just draw on this. Screw it, I'm done with the Etch-A-Sketch. I can't do much with that anyway. I'm not gonna create Bob Ross because I don't have as much control over that. Now, stay with me, stay with me. This is so cool, this is so cool. All right, I love that idea of the Etch-A-Sketch because then you can actually like just see somebody controlling the velocity at which they're turning those knobs. And then what is actually showing up on the Etch-A-Sketch screen are the points that I'm creating as I turn those knobs. So is one knob a function of the other knob? Not necessarily, because there's a thing that I'm controlling the knobs, correct? So they're actually a function of me. I am the real behind the scenes manipulator, controlling all the points. I'm constructing all the points. Okay, this is kind of weird, I know. I want you guys with me. So normally we think of a function as if X changes, then Y changes. Now we've got the idea, if the rate at which I turn a knob changes, that changes where X is, and the rate at which I turn this changes what Y is. So they both depend on me. They don't really immediately depend on each other. Oh, geez, what are you talking about, Jeff? All right, I really want you guys with me. All right, so coming back up here. So what I was saying was if I spin the X knob twice as fast as the Y knob, so how would I capture that idea? Well, let's say that the Y is equal to T. Then the X would be equal to 2T. That's amazing. T is the parameter. So let me see, what's a good example of this? Now I can't get that idea out of my head. Okay, Jeff. Okay. So let's say you've got a certain kind of tire and your friend's got a certain kind of tire, right? Two different kind of tires. Are they going to wear away at the same rate? What's a better example, Jeff? I can't think of one. Fudge. Well, what about why am I unable to think of a? All right, a spring versus another spring, right? Pretend like those are springs. One might require more force to make it compress. Does that make sense? Have you guys ever played with springs much? There's a certain parameter. There's a parameter that defines kind of like how much force it takes to compress a spring. And it's actually, believe it or not, it's K. It's called Hooke's law. So one spring might have a big K and another spring might have a small k. And that would be a parameter that would help me figure out with so much force, it will compress by so much. Oh my God, I just had somebody log out. I understand. I really want you guys with me. All right, I'm not going to suddenly teach you physics. So the name parameter is, it's not really a variable in and of itself. It is the condition upon which I can create other functions. So if you got a different car, wouldn't it have a different gas mileage? So for a specific car, you could set up an equation that relates how far you can go and how much gas is going to take. But between different cars, it might have a different parameter for the gas mileage. So an equation for a different car would have a different number in it compared to the gas mileage. So gas mileage would be like a parameter. So it is something that changes for every car, but it does, the true variable is the distance you go and the gas you use. So parameter is not in itself a variable, really. It's what controls everything else. So this is what's controlling both of these. So let me ask you this. All right. Let's do something. So to make XY points, I actually need a TXY table. If T is 0, X and Y, of course, are
0.
0. Is everybody with me? So at time 0, this is at 0, 0. When T is 1, this is 2, 1. So it's at the point 2, 1. So I am making points, but I'm making points in a way that we never have before. I'm not using X to figure out Y. I'm not using Y to figure. I'm using some third behind the scenes dude to figure these out. So at 2, this would be 4 and 2, and so forth. So I'm creating points that deal with X and Y, but using a behind the scenes parameter. Now, to be honest, in this case, you totally can eliminate the T. What is T? What is T? T is Y, correct? Isn't that what this says? Y is T. So I can rewrite this. X equals twice T, but freaking T is Y. Bam. So Y is 1/2 X. That's all this thing is, isn't it? If X is 2, Y is 1. If X is 4, Y is 2. Bam, bam. All right, not very impressive because it's a very silly little, it's very simple, very simple. I almost don't even need a freaking parameter to capture this relationship. Okay, maybe. Let me show you something else. All right. So what, oh, sorry, are we good? All right. What if I had extreme control as I'm twisting the knobs? What if I had a control so I could control this one with a cosine function? So as time goes by, this is how I'm turning the X knob. So I turn it to 1, and then I turn it to -1, and then I turn it to 1. Right? Where am I coming up with those numbers? What does cosine go between? What does cosine go between? Least to highest? Yes?
-1 to 1.
-1 to 1. So the x's are going from -1 to 1 to -1 to 1. What are the y's going to do? I don't know. I haven't told you what those. So that's sine c. So what are the y's doing? They're going from -1 to 1, -1 to 1, right? Why did I make my scale so weird? I don't know. All right, there we go. All right, it's a little bit better. All right. But I know, stay with. They are doing that at the same time. So as x goes back and forth, y is also going back and forth. So actually together they make a circle. You might have expected that. I don't know. So if I have t, let's get some big points in here. At 0, what is x? 1. And what's y? Sine of 0 is
0.
0. All right. I know Rio and Charles are here. Is anybody else here? Okay. Thank you. Project. Yeah, Charles, exactly. I mean, no, trust me. Let's just talk about the concept. The uses of this idea of parametrization. Parametrization. All right, that's probably it. The uses of it are insane, wide ranging. So you can see in the chat, Charles said, what did you say? Projectile motion. Yes, totally. You can control, if you're controlling something, you actually need 3, X, Y, Z, but they could all be controlled by a single parameter T. Yes, of course, totally, yes. All right, what about if I put in there pi over 4? Of course, cosine and sine at pi over 4 is what? What's cosine pi over 4?
Rad 2 over 2.
Oh, thank God. All right. Rad 2 over 2, which is roughly 0.7. And of course, at pi over 2, it's just turning this around because now sine is maximum, cosine is minimum. So let's see what we got. Now if I just plot these points, 1, 0, 0.7, 0.7, 0, 1, you can see it's already stretching out. It's already, now here's the trick. Here's the cool thing. Do you guys see how if I keep going, I will definitely get a circle? Does that make sense? Does that make sense? And you can actually do something that we've never been able to do before. You can show a direction of motion. As time progresses, if you consider this to be time, isn't it moving in this direction? Just make it and then do this. There you go, buddy. Good job. You can do it. You can do it. Can you do it? You did it. Yay. Okay. And then, of course, it's going to keep tracing out over itself. Now watch this. You ready? This is so cool. How do I eliminate t? How do I eliminate the parameter between those two? Such a cool thing. Never forget your trig identities, kids. What's the easiest identity between cosine and sine?
Is it if you?
What was that? That was very trippy. Say it again.
It's both of those.
Can anyone tell me any identity that involves cosine and sine? Any identity? Any identity
Cosine squared plus sine squared.
equals 1. Okay. So what's x squared plus y squared? Isn't that cosine squared plus sine squared? Yes. Isn't that and that's equal to 1? Yes. What is that the equation of? You guys see that?
Circle.
Circle the radius 1, which is what I just drew. Woohoo! What you lose when you eliminate the t, what you lose is information about how this is actually moving. I got a bit of a party in the back. Oh well. Right? When you write this, you've lost the direction of motion. Maybe. Nope. It sucks. You suck, Jeff. All right. What about this? Let's take a step back. What about, well, I had an example put together, didn't I? Yeah, let's do that. All right. We're not going to graph this one. I just want to kill t. Can anyone see the simplest way to kill t between these two? If only I knew what t was. Not this t. This is good t. Might be a Long Island iced tea. I don't know. Do either one of those equations say t equals? No. If only one of them did, that would kick so much ass. Because then wherever there's a t in the other dude, I would just replace it. All right. Can I solve this for t? Of course you can. What do you get when you solve that for t?
Y plus 1.
Yeah, so you get t is y plus 1. So how can you rewrite this? X equals 1 minus t squared. So if you do that, you'll actually end up with negative y squared minus 2y. If you don't believe me, do it yourself. Nah, leave me alone. So this actually, I don't know if anybody realizes what this looks like. This would be a sideways parabola, right? All right. So when I ask you to eliminate the parameter, you think of this as a system of equations. So if you can solve one for t, you can plug it into the other one. Now, if you can't do that, or you don't want to, like with cosine and sine, you might try to think of trig identities or something else. All right, so let's do this. Let's look at, oh shoot, I need to make this active. Mouse, wake up. Okay. Oh, where are you? Here we go. So in a minute, let me open this up on Canvas. And under Unit 10, you should see something called Parametric Equations on Canvas. Let me show you. Let me become a student. There we go. If you go down to Unit 10, Parametric Equations right there. All right. I'm going to open this a different way so it's a little easier for me to work with. But you guys see this yummy, so yummy. Oh, this is so yummy. All right, here we go. Hold on. Being extra creepy today. No, Jeff. Oh, shit. What did I just do? Okay, thank God. All right. Whew. You hit the wrong button and everything goes to hell. Okay, let me find this. Where's my parametric? Where'd you go? There you are. Where'd you go? There you are. Haha. Can't escape me. All right. So let's take a look at this. I need you to help me. I need your help. Please, please help me. Oh shit, I need this thing's help. This is compared to some of the stuff we've been doing. This is really not that bad. And the other stuff we've been doing isn't that bad either. Anyway, stop it. So how does this stuff work? So notice something I've told you that's very, very important here. What is t allowed to be in number one? What is t allowed to be?
-4 to 4.
Yeah, you can only use these values. Thank God. All right, so let's try to plug some of those in and see what happens. So if I plug a -4 in, take a minute and figure out what x is. Don't say anything yet. Shouldn't be too crazy, right? When you plug a -4 in here for t, you get -2 pi. And of course, what is sine at any multiple, any whole number multiple of pi? Sine of 2 pi, sine of 3 pi, sine of -5 pi. Is sine gonna like it there?
0.
Yeah. Is that cool, everybody? At any multiple of pi, any whole number multiple of pi, 2 pi, 3 pi, 4 pi, it's not gonna like it because there's no y, it's all x here. So this is gonna be 0. And then y should be easy to plug a -4 in. -4 squared is 16, half of 16 is 8, -4 is 4. I like it. Why don't you guys go ahead and finish that up? I'll just sit here and hope that most of you are there and doing this. Am I recording? Yes, okay. Thank you. Oh yeah, that's right. Yeah, I'm curious. And there's only it's like only a continue button, right? There's no like screw this and then it kicks you out. I mean, it's either continue or have the little thing up on your screen the whole time, I think, right? Oh, there is an option to just leave. Well, that's neat. I like that. Either, yeah, but the thing is I never record you guys. It's always just me. Okay. Oh. Yeah. I would hope that if anybody had any problems with me recording our session, something would have come up before now. Okay. So I'm going to slowly catch up to you. So if I plug a -3 in, that'll be 4 sine of -3 pi over 2. Oops, what's happening? Are you kidding? Oh, okay, yeah. For a minute there, I thought you were angry at me. Shit. Let's see. Now stay with me. So -3 pi over 2 would go back to here. Sine loves it there, so it's going to be 1, so it's going to be a 4. And after you've done a couple of these, you'll see a pattern, right? And do you see how I'm just sticking with the x? So I only have to worry about one function at a time. Let me just do all the x's. So when I plug a -2 in to here, that's going to give me -pi. Sine's not going to like it. It's 0. When I plug a -1 in, now that's -pi over 2. And at -pi over 2, it's down here. So it's -4. -1 times 4 is -4. Is anybody not with me as to where these numbers are coming from? You can always private message me and say, I am so lost, dude, math boy. explain yourself better, earn your damn money, math boy, right? Okay. I appreciate that. Somebody's being honest, but they're being nicer to me than I am. I like that. All right, so let me slow this down a second and let's really analyze. I got some room here, so I might as well use it. So in this first one, we did 4 times sine of pi times 4 over 2, correct? Oops, sorry, -4. All right, so I was plugging a -4 in. Is that cool? Plug a -4 in for t. So that's 4 times sine of -2 pi. Is that cool? And of course, -2 pi is just the x-axis. Any integer multiple of pi will be on the x-axis, and sine will hate it there. It'll be 0. So that's why that's 0. Is that cool? Now, if I plug a -3 in, I'll get 4 times sine of -3 pi over 2. -3 pi over 2 is here. Is that cool? I mean, does everybody follow each step? Let me know the minute I do something that doesn't make sense. This is where sine likes it. It's +1. So +1 times 4 is 4. And then when I plug a -2 in, I get 4 sine -pi, which is 0 again. When I plug a -1 in, I get 4 times sine of -pi over 2. -pi over 2 is here. And that's why it's -4. So now you see the whole thing, right? Now it's just going to keep repeating 0, 4, 0, -4, 0. If you don't believe me, you can plug something in, but that's the beauty of trig functions, right? Once you see their pattern, they just keep going. All right, let me stop for a minute. There's nothing wrong with doing this work. You don't have to get it all done in your head. That's fine. All right, if anyone's still lost, please tell me now. Okay. Of course, the more you've done what I asked and actually memorized your trig function values, the easier this should be. And there won't be trig functions. See down here, number 2? See how there's no trig functions there at all? So parametric equations doesn't have to use trig functions. It's just one function they can use. This one should be easier, right? So -4, I already did. -4 squared is 16, and 1/2 of 16 is 8, minus 4 is 4. When I plug a -3 in, -3 squared is 9/2, minus 4 is 0.5, right? 9/2 is 4.5, minus 4 is 0.5. Is that cool? Okay. When I plug a -2 in, -2 squared is 4 divided by 2 is 2 minus 4 is -2. When I plug a -1 in, I get 1/2 minus 4 is -3.5. When I plug a 0, I get -4. Is that cool? Right? When I plug a 0 in, I get -4. When I plug a 1 in, 1/2 minus 4, and now it's going to start to repeat itself because it's a parabola, yes? You guys see how I've discovered its vertex? And now it's going to start to repeat itself back up. So locally, parabolas feel like trig functions around its vertex, but I mean, anyway, that might be too much to say. All right. And then it's just going to kind of repeat from there. And again, if you don't believe me, or you want to double check, if I plug a 3 in, of course I'm going to get the same thing as when I plugged a -3 in, because the first thing I do is square it. Is that? So that's all I'm doing is plugging values of t in to each thing one at a time. As much work as you got to show yourself to get it done, do that, right? But now when I'm going to go graph it, which thing here do I not give a shit about? Which thing here do I not give a shit about?
T.
T. T never shows up explicitly, right? If I watch a rocket flying through the air, I can see its X, Y, and Z. You guys with me? I can see how high up in the air it is. I can see how over this way it is, and I can see how over that way it is. Can I see time? No, if you can, you took some really weird drugs or something, right? Like time is literally slipping through my fingers. All right, be careful with that stuff, kids. You might start to understand math if you take the wrong stuff. All right. So now all I've got to do is plot these points. But what I need to do is I need to capture the direction of motion. So what the shit do I mean? So let's plot these points. So 0, 4 is right up here, right? So this is going to be, I'm not even going to put the scale. It's just a regular 1, 2, 3, 4, 5. I think it's going to fit everybody. Yes. So 0, 4, it's right there. Beautiful. Oh, thank God. Just something concrete. Put a dot there. Then it goes to, so again, you got to ignore the T's. You can even rewrite the points if you need to, so you don't suddenly look at T for some reason. So the next thing I'm going to do is 4.5. So 4.5. There it is, buddy. You did it. You did it. You did it. Then it's going to go 0, -2. So this looks like it's probably doing this. And if I wasn't sure, I could do some in-between points, right? If I needed more resolution, I could try to plug in -3.5 for T, -2.5 for T. Do you guys understand what I'm saying? If the steps were too big, if I wasn't sure what it was doing. I don't know. Is anybody completely lost? You got to let me know. So how, in the past, how did I make a bunch of points to plot something? I picked a value for X, I plugged it in, and I got a value out for Y. We're basically doing that, except X and Y individually are dependent on T. So now when I pick a value for T, I construct an entire point from that. These are the points I plot. This is the behind the scenes thing. This doesn't show up ever. There's no T-axis. All right, I love you guys. Okay, so let's keep going. -4, -3.5 is the next thing. So -4, -3.5. -4, -3.5. It's going to be right there. 0, -4. It's going to be right there. And then +4, -3.5 will be right there. So now it's going, whoa, trippy-dippy-doo, trippy-dippy. Wow. Sorry, you can make whatever sound effects you want. So I can pretty much guess what it's going to do. What do you hope it's going to do, or else it's going to feel like the beat never dropped in the song and you're going to stay awake all night. No, nobody's ever had the experience. Doesn't it look like it's probably going to kind of complete this? Don't you hope it's going to do that? So let's see. Where did I leave off? Here, 0, -2. So it's here again. So, wow. -4.5, -4.5 is right there. -4, comma 0.5. And then it goes back to 0, 4. It goes back to here. So sure enough, look at this funky ass shape we have constructed. Don't use that thing, Jeff. Well, actually, it's not that bad. It's terrible. It's terrible. It wasn't that bad. All right, Jeff. This is probably going to be worse. You just wait and watch. Have some. Yeah, that's way bad. Sorry, guys. Sorry. Hold on. I can't let myself go. That's got to be the extreme value over there. And then it comes back up there. And that's I can live with that. Okay. This looks a little bit like the mushroom people from Mario. The outline of it.
The Goombas?
Yes. Although that we got to be careful about that word. They chose a very poor word for that. It's not really in good taste. All right. What do you guys think about that? I mean, is that It's not difficult, for sure. It's not difficult to do this. There's an extra layer of keeping track, and I didn't do a good job back here, keeping track of the direction of motion. Now, to be honest, what do you guys think? Do you think it traces? Now, let me see if you guys are cool with this. Do you see how it's contained? Jeff, let's try this again. Let's do this in a different color. Do you see how it's contained? How can the eraser be a different color? Okay. Do you see how it's contained between here and there on the x-axis? Why does that make sense? What's controlling the x-axis? What function? Hello? Yes?
It's a trig function.
A sine. Yeah. You got to be careful because tangent's not bounded in the output, right? So it's a sine function that's bounded in the output. What is y controlled by? A freaking parabola. Is that bounded? Is a parabola bounded on both sides? No, it's just bounded on one side, isn't it? So what do you think would happen if I let t go beyond -4 and 4? Is it going to be able to go any more this way or that way? Ever? Is it going to be able to go that way or this way anymore ever? Yeah, y is going to grow. Y is going to grow. So it's going to be doing this thing up and down forever on the y-axis. So stay with me. Let's do this in the calculator. How do I do this? Oh, Jeff, you complete doofus. Sorry, Jeff is a complete doofus. Just wanted you guys to know that. I just did all that work using the wrong drawing tool. So it all just disappeared. Yay. All right. God. So let me open my calculator. Oh my God. All right. Sorry. I should have done all this on the board. Oh, well. So if you got your calculator, kids, do you remember how to change to polar coordinates? Where do you go to change to polar coordinates? Anybody remember? You go to mode, there's polar, and of course, right before that, parametric. Bam. So now if you hit parametric and then you go to y equals, you get this kind of stuff. Ooh, I got neat stuff in there already. Chumbawamba. All right, so there we go. So I can put in here, I have completely forgotten, 4 sine, what was it, pi t over 2?
Yes.
And I love it when you change modes. This is your all-purpose variable button. It changes to theta when you're in polar. It changes to t when you're in parametric. Blah blah blah. Okay. And what was y? Y was 1/2 t squared. Is that right? 1/2 t squared minus 4. Is that what that was? Nobody's gonna help me. Nobody's gonna help me. Damn. All right, I'm all alone. Yeah, that's what it was, Jeff. Okay, Jeff. Now, if I hit window, I can control the T min and the T max, and I want that to go from -4 to 4, yes? And I don't know about my, oh, geez. Let's make this the same as the paper. Went from -5 to 5. And -5 to 5. There we go. So that's the same scale as I had on the paper. Yes. So see what this looks like. Hello, that was fast. Let me slow that down a little bit. If I make this go stepping a little bit slower here. All right, that's a little bit easier to. Oh, poor little dude didn't quite make it. Yeah, he has some resolution problems sometimes. But now watch. So that's basically the same shape we got. Yes. So what happens if I let t, let's say it goes from -8 to 8. I'm going to have to zoom out a little bit. I'm going to have to make my y max. Let's make it 20 just to be careful. There we go. Look at that. You guys with me? You guys with me? So this piece is what we did. And it makes sense that it's bounded in the x direction because x is controlled by sine. But in the y direction, it's trying to be a parabola. Okay, I like it. I like it. It's kind of neat. So, I mean, you could do all kinds of weird shit. Again, if you wanted to, you could just play around with this a bit. You could put in there sine of 3 theta t, and then you could put I don't know, what do you want to put in there? 4 cosine of t. Let's see what that looks like. Oh, look at that little dude. Look at him go. Now, why is this so much more contained in all directions? Why is this so much more contained than what we did before? See the function?
Yeah, because of cosine.
Yeah, now they're both bounded, sine and cosine. So the y goes between -4 and 4, and the x goes between -1 and 1. Yeah, I like it. I like it. And of course, if I make the y plus 4, it'll just move the whole thing up 4. Woo! So one thing parametric equations does for us is it's easier to control the details of the resulting graph, right? There are so many things you can do purely mathematically and practically easier with parametric equations. Does it make everything easier? No, it makes some shit hard as hell, right? So one thing you learn as you go through math, you learn new ways of representing the same kind of stuff, new ways of representing points, new ways of representing equations. You don't do it just because we want to make you do something. We keep you busy. It's because humans, we want to know more ways to do things, because this problem might work better parametric, and this problem might work better polar, and this problem might work better rectangular, and this problem might work better in some shit I don't even know about yet, right? So as you go through math, you're going to learn other, more, and different, even some in 3 dimensions. There's some shit called spherical coordinates, which is exactly what you would think they are. They're all about spheres. So it's like polar in 3 dimensions, right? So that's some neat shit. Okay. Enough of this. Enough of this, Jeff. All right, let's go back to the sheet. That's now blank for me. Oh, it's too funny. I should use this someday. Can you guys, you guys do this. I'll just sit here. I'll just sit here and shut up. You guys do number 2. Well, yeah, this is cool. I forgot about this one. I like it. I call this one math graffiti. I'm gonna start to catch up to you guys. -1 minus 3 times -1 squared, that's -1 minus 3 is -4. -2 minus 3 is -5. That's easy, that's 0. That's -3, that's a nice one. 1 minus 3 is -2. 2 minus 3 is -1. 8 minus 12 is -4. Did I do that right? Yeah, I think so. And then where am I at? 4 minus 3 is 1. And then 27 minus 27 is 0. And Jeff, what happened to your brain? There it is. Okay. Now see how I left a little room in between in case I want more resolution? Okay. So again, I can use a nice normal scale. So I can use ones all the way around. That's nice. And I'm really, one of the easiest things to get in a trap of is to start plotting points and then starting plotting 1, -2, 2, -4. Do you see what I mean? You've really got to make sure you focus on these are your points here. But did anybody else get those same numbers? Are you guys getting the same numbers?
Yes.
Okay. I always like to know that I'm doing it right also. Math teachers want to know that too. All right, let's see. Thank you, Matt. So now you got to do is plot the points you made. You got to be a little bit mindful about it. So -4, -5. Now, what do you think about the next step? The next point is 0, -3. That's not too desperately far away. So maybe I don't need more resolution. But just to show you what I mean by that, what do I get when I plug a -1/2 in? You might need to help me out with what do you call it? Calculator. Let me see if I can do this in my head. -1/8 minus 3/4 is -6/8. It's -7/8. Is that right? I think so. -1/8 minus 3/4. Yeah, -7/8. So like -0.875, like -0.9, I think roughly. And then that's going to be -4. Neato. So -0.9, -4. So right there. So do you see how that gave me a little bit more information about the curve between these two? Because don't forget, we use -1, 0, 1, 2, 3. Is there really anything special about those numbers? No. We think there's something special about them because they're 0.0000 forever, but there's nothing special about them. And when we go from -1 to 0, we are skipping a lot of possible inputs. So does that make more sense what I mean by resolution? All right, so now I know it seems to be curving like this. Jeff, let me try this again. Curving like this. Okay. Thank God. All right, let's see if I need any more help. So -2, -1, -2, -1. So it seems like it just kind of keeps going. I don't know if it comes out here at all. Let's try to plug in a 1/2 just to see how much I can annoy you. Let's see, 1/8 minus 3/4. So that'd be -5/8. So that's -0.6 roughly. And then 1/2 of 2 is 1 minus 3 is -2. Well, that's not that bad of a point. So -0.6. -2, it's almost a straight line, but it does look like it's a little bit of a curve up. Oh, pen, you, okay, that's fine. So maybe I could have gotten away without doing those half points, but you always have that option if you need it. -2, -1, we just did, -4, -1. I'm sorry, -4, 1. So that's right there. And let's go ahead and put 0, 3 is right there. So what it looks like it's doing is it probably curves this way, and you get a beautiful letter S. Yes? Are you guys with me? Did you ever think you would be able to figure out the equation for the letter S? I mean, is that even a question you had in your mind? What is the equation for the letter S, Jeff? Well, this is one option. This is one. And now you start to think, when a computer constructs when you construct a different font, don't you have to tell the computer how to construct those symbols? Yes? If you alter a font, that changes the parameters the computer uses to construct the symbols that represent our letters. What? Yes? So that's a very, very simple use of parametric equations, is controlling font. Controlling how, and there might be certain parameters. So you might have a set program for your generic letters, and then you have one font changes these parameters, and another font changes these parameters, and another font changes these parameters. And it changes the slight different tilt and a slight different compression or extension. Yes, maybe. Because if I go in here and I put 4 here instead of 3, is it still the letter S? Is it stretched? You know, that's interesting. Anyway, maybe just a bit. If I kept, now of course I constrained it by quite a lot. And now to be honest, if I just went forever, it would just be kind of a boring cubic function. So I really just chopped out the part that made an S to be more interesting, but it's still kind of neat to see it happen. Has anybody tried part B yet? It's not too hard to do this. Eliminate the parameter, kill the T. Right. It's kind of like a history lesson. Throw the T into the ocean, boys. No taxation without representation. Austin, you all right, man? You're a little sleepy. That's all right. I understand.
Yeah, I'm doing all right. I'm hanging in there.
All right. Just a little hint, a little life tip. If you're having trouble going to sleep at night, just play my videos and you'll drift right.
That's not a bad idea, actually.
Yeah, I'm not joking. Just play the video and you'll hit, Mr. Well, yeah, you're out. It's better than reading Consumer Reports even. It's amazing.
It still makes more sense to me than the last section we were doing.
Okay. All right. Because as a student, I'm sure you guys are like, okay, this got really weird and we're not done yet. What's the next level of weird? And it's like, oh, good. We kind of took a step back. This isn't that bad. So has anybody figured out part B yet? How do you, what's like the first step?
Solve for T.
Yeah, I can solve for T in Y. So I get T as Y plus 3 over 2. And then I can plug that business into X. Jeff. Oh, now look what I'm going to do. I'm going to be neat. I can take a Y plus 3 over 2 out squared. And then I get Y plus 3 over 2 minus 3. Anyway, you guys can do this however you want. You can do all this if you want to. So here I get 1/4 of Y squared plus 6Y plus 9 times 1/2 of Y plus 3 minus 6, so Y minus 3. Well, that's neat. Did I do that on purpose? I think I probably did. So this will be 1/8. I have no idea if you guys are with me. Does this work? I think it does, doesn't it? No, it's not quite right. That's true, Jeff. Good, I tried. And then whatever the hell all that shit is, I don't really care. Y cubed minus 18 plus 9, so minus 9Y squared. No, you didn't do that right. You left your squared out, Jeff. Minus 3Y squared plus 6Y squared is plus 3Y squared. And then minus 27. All right, barf. All right, so that's just busy work. But that's what you try. That's the first thing you try is, can you solve easily for t? And then just plug it in the other dude. If you cannot do that, you try to get a little creative. If it's trig functions, you think about identities, right? Oh yeah. All right, let's try this. Try to plug that in your calculator. I don't even remember what that was. I created this a while back. Let's try to plug this in our calculators. Let me see, I made mine here. Here we go. Shazbot. All right, get over there. I'm really curious what past Jeff did here. Let's see. Two sine plus 3 cosine. Okay. 5 cosine. Well, that's kind of silly, Jeff. Oh well, that's too bad. Oh yeah, that's so cool. Past Jeff. Okay, I forgot all about that. Is anybody able to do that? Plot that in your calculator. Anybody? What'd you get, Isabel?
I
I can't see. I'm sorry.
don't know
There it is. Yes. Okay. I like it. So like an ellipse that's been turned sideways. Isn't that cool? Jihad. Doesn't it look maybe like a orbit of a planet, maybe something? It's a little extreme. This is true. Maybe orbit of a comet. Okay. All right. Anyway, all right. So that's pretty cool. So now you can do diagonal ellipses if you wanted to. You could change the numbers in there and get it and see if you can make it turn the other way. Change which one sine and cosine. See what effect that has. I mean, there's a lot of cool shit you can play with. If you're really, really bored and you have your calculator, you can play with parametric equations. All right. I think that's plenty. So let me know if you need to hang out. Otherwise, you're free to go. And I think tomorrow we'll finish up chapter 10 and maybe take a little step into 11, but we'll have to wait and see. We got vectors coming. Vectors, kids. Vectors. Yay. All right. If you have a question, let me know. If not, you can go. Let me see.
Thanks, Professor.
Sure.
Thank you.
Sure. Paul.
Good night, Professor.
See you. Let's see, Paul, what happened with you? I kind of remember something. Let's see.